given assignment calculus that we have to solve. There are two tasks that we solve by me, which are problem number 1 and problem number 3. For task 2, I will solve problem number 2. So here I will demo the quiz and solve the quiz.
Okay, next for this task, solving for the relative minima and relative maxima. So for each this problem, we have to find all the points of relative minima and maxima. Furthermore, we have to use GeoGebra to produce the graph of the function. So problem 1 is y equal to x cubed minus 5x squared plus 7x minus 5. So we use GeoGebra to produce the graph. So y equal to x cubed minus 5x squared plus 7x minus 5. So we enter, we get the point. Here we can see the maximum point, maximum point is when the x is 1, the y is negative 2. Same goes to minimum local point when the x equal to 7 over 3, which means it's between here, and then y is negative 86 over 27. So here. So that's all.
Okay, for task 1, solving for relative minima and relative maxima. So for the first problem is y equal to x cubed minus 5x squared plus 7x minus 5. So first step, we have to do the first derivative for this equation. So y prime equal to 3x squared minus 10x plus 7. So to find the critical point, we have to let x equal to 0. So 3x squared minus 10x plus 7 equal to 0. We get here is 3x minus 7 and x minus 1. So we solve this equal to 0 and we get x equal to 7 over 3, and this one x minus 1 equal to 0, we get x equal to 1. So the critical points are 7, 3 and 1. So next we have to do second derivative for check the point of this point either upward or downward. So for second derivative, we do is just now the first derivative is y equal to 3x squared minus 10 plus 7. Oh sorry, 10x. Okay, so for the second derivative we get 6x minus 10. So we have to to check this, we have to do y prime x equal to 0. So here okay, this one to check whether it's inflection point, where is it? So we don't need to do this actually. So to check the point whether it's curved downward or upward, okay, if we let the f point double f second derivative f y second derivative 1 equal to 6, we substitute the critical point inside this equation, so then we get -4. So this means the graph is curved downward. Okay. For another point is 7/3 is we substitute in the equation, so we get 4. Okay, right? So we get this one, it's curved upward. From here, we can conclude at 1 okay, at point 1 there exists maximum point. So at 7/3 there exists minimum point. Okay, so how we want to know the coordinate? We just substitute this point inside the original equation. So here f1 equal to the original equation is 1 cube minus 5 1 squared plus 7 minus 5 equal to -2, while f, the x is 7/3, we get here we get -86/27. So the conclusion for this equation based on the coordinate is at 1, -2 is the local maximum point, and equals to at 7/3 point and point it is -86/27, this local minimum point. So that's all.
Well, hello there. My name is Citraril, and this is a video for the assignment that was given. So as you can see, that's my matrix number 187379. Above that is my name. Okay, so this is just to prove that I'm the one doing the calculation. Okay, so for now I am given the task. I'm going to show the solution for task 1, problem 2. Problem 1 was solved by the other group member that I have. So we'll jump right straight to the question. Okay, as you can see here, the question given is you have to find all the points of the relative minima and maxima, and then I have to use GeoGebra to produce the graph of the function. Well, let's just to confirm the result and give you a better view of the problem. So this is the question right here: y equals to x3 minus 6x squared plus 9x plus 1. So if I plot the graph, it will look something like this. Okay, from here you can see there's like an arch that arch upwards. So that's the relative maxima, and then you see another arch which is arching towards downwards, and that is the relative minima. So that's the point that we want to find from the given equation. So how do we do that? Okay, let's jump straight to the solution. So as stated, the question gives this equation, and we have to find the relative maxima and minima. So what I would like to do first is find the y prime and the y double prime. So we'll go ahead and do that. Y prime equals to 3x squared minus 12x plus 9. And then we go ahead and differentiate that again and get the y double prime, 6x minus 12. So now that we got the y prime and y double prime, we'll go ahead and get the critical points of y prime. We don't want critical points of y double prime. We want the critical points of y prime. So to get that, we will get the equation and then make it equal to 0. Then we factorize. So we then find out that the critical points is x equals to 1 and x equals to 3. So since we got the critical points, we want to know if these 2 points are either local maxima or local minima. So either one of them is minimum, and this both can be either local maxima or local minima. So we want to find out which of them is which. So how do we do that? We use the double prime here. So what we do is we're going to substitute the x value in the double prime equation. So let's do that first. Y double prime. I'm going to cut it short. I'm going to cut it short. So I'll just do y double prime. So we do for 1 first. We substitute 1 inside the equation first. So I'm going to cut it short. So I'm not going to write the equation. I'm just going to straight away write the answer for it, because I'm sure that's understandable how we substitute and stuff like that. So once I substitute that, I'll get negative 6. If I do that, for the other x, I'm going to get a 6. Okay, what does this mean? Okay, if we want to determine whether this the critical point is a local minima or local maxima, what we're going to do, we're going to see what is the sign, what is the value, the sign that it holds. So we can see that for the critical point 1 has a negative, and the critical point 3 has a positive value. So if it's negative, it is a local maxima. You can see. And then if it's positive, it's a local minimum. And that's how you decide whether this critical point is either local minima or maxima. So now that we found we found local maximum and local minimum, what we're going to do is we're going to find the y coordinate for it, because the question wants us to find all the points. So the points require x and y. So we'll go ahead and find the y coordinate. So that's simple. We're not going to use the y prime. We're not going to use the y prime or the y double prime. We're going to use the y equation right here. So I'm going to cut it short, and we'll find that y1 is equals to 5. As for y3, you'll get 1. And therefore, we can conclude that the local maximum is 1, 5, while the local minimum is 3, 1.
Okay, for problem number 3, give an example function fx where f double prime 0 equal to 0 and there is a relative maxima at x equal to 0. So here we can use create an example that to find the relative maxima is equal to 0. So we found out it's negative 4x squared. We can find it here. So here is the where the relative maxima is 0. Okay, the solution. That's all.
First, for the task 1, problem 3, the question is give an example function fx where f double prime 0 equal to 0 and there is a relative maxima at x equal to 0. So we try out a example is fx equal to negative 4x squared. So from here, f prime x is negative 8x. So okay, here we can if we let the want to find the critical point here, let f prime x equal to 0, x equal to 0, x is 0. Okay, so for the checking it, we make f double prime x is negative 8, which means fx prime 0 is 0. Okay, the graph is stop.
Hello there, it's back to me. So for task 2, problem 1, so let's have a look at the question. Okay, it is stated that let a and b be two positive numbers. Suppose that a plus b equals to 9. Find a and b such that ab squared is maximum. So two things you got to take note right here. So let's go to the solution. So there's two things that we want to take note right here, and that is the equation a plus b equals to 9, a b squared. Okay, this equation is what we call the constraint, and this equation is the optimization equation. We also have to take note that a and b are positive numbers. So the goal of this is that let m be the optimization equation. The goal is to differentiate this equation and then finding the critical value, substitute that into this equation, and we'll find the value of a and b. Let's just do it. Okay, so in order for me to differentiate this equation, I need it to be in one term, meaning that either a or b. So what I'm going to do is I'm going to substitute b with a value. So I'll go ahead and do that. No, I'll substitute a with a value, which is easier because I don't have to go through this. So a plus b equals to 9, then a equals to 9 minus b. So I'll substitute that, and we will get m equals to 9 minus b squared. That equals to 18 b, sorry, my bad, 9 b squared minus b cubed. Okay, so we're going to differentiate that. You'll get 18b minus 3b squared. So to find the critical points, we're going to factorize it, and we'll get 3b 6 minus b, and we'll equate that. So equate that. Bear in my handwriting, I'm bad at my handwriting. So equals, we're going to equate that to 0, and we're going to find the critical points, which is b equals to 0 and b equals to 6. Okay, so one thing you got to take note here is that previously I said that a and b must be a positive number. So if you're going to find b and you're going to choose a value between these two, you have to choose the one which is positive, which is not 0 and 6. So we will take b equals to 6 as our value. So we've got our b value. We're going to find our a, and that's simple. We already have our equation. A equals 9 minus b. You're going to substitute b into this equation, and hence our equation is, our a is 3. So to put short, to conclude it, a equals to 3, b equals to 6.
Okay, for task number 2, problem 2, the question is, suppose that your house has a garden along the side of your house, and you want to fence 3 sides of the garden using 720 meters of fencing. Find the maximum area of the garden that can be fenced. So here we can see actually the garden is attached with the house. So house is here and this is the garden. They say 3 sides. So this one and this one we let as we say x equal here length of each of the other 2 sides is same. Okay, so the same, and this one is equal to y. We let, okay, this one we let x and y actually. We let y for the length of side parallel to the side there is no fence. Okay. So from here we can see the constraint equation. Okay, constraint equation we get is y plus 2x equal to 720. So how to find the value of y, because we want to say the unknown to find it. So here we can say y equal to 700 minus 2x. Okay, from here, next, for optimization equation, we can get the formula of the area is, from the formula of the area, we time x time with y. So here we have 2x, right? Okay, sorry, it's not 2x. X time with y. X here, and the value of y we get 720 minus 2x. So we open the bracket, we get 720x minus 2x. So how to find the maximum of the maximum area? So we have to derive it from a prime. We get 720 minus 4x. So to find the maximum area, let ax to 0. So 720 minus 4x equal to 0. 4x equal to 720, and x equal to 180. So here we get the x is 180. So based on the maximum and minimum, we have to find it. It's either positive or negative, maximum or minimum point. Okay, we have to find that. So here is 180. So we let any point between before 180 and after 180. For example, we take 150 and 200. So use this number and insert to the equation a prime. So a prime 720 minus 450, we get 170. So this is positive value, so it's a upward. Okay, based on the first derivative, want to find the local point. Okay, for next one, for the next point, 200, we got negative value, so it's a downward value. Downward. So it's coming like here, this here. Okay, so we want to find the maximum. So want to find the value of y, we have to use y, submit the value of 180 just now into the okay, use the substitute the x value 180 into the constraint equation. So where is y equal to 720 minus 2x just now, constraint equation. equal to 360. So the area got is 360 times 180. So the area is 64,800 millimeter squared. Maximum. Why we have to find this? Because we want to check whether this is where the point is the maximum. We want to check whether the 180 point is really a maximum point. Okay, so from here we can conclude that 180 is a maximum point, so that's why we substitute back inside the constraint equation to find the value of y, and then we substitute back the value of x and y into the formula to find the area. We have to time x and y, so we get here the area of the maximum area of the garden that can be fenced is 64,800 meters squared.
Okay, back with me for task 2, problem 3. Let's go to the question. Okay, so this is a bit complicated, the question, but the solution is just almost the same. So in an orchard, there are 4 durian trees that produce 20 durian each tree. For each additional tree in the orchard, the production of durians dropped by 2 durians per tree. Find the number of durian trees to be added to the existing orchard in order to maximize the total production of durians. So basically, let me show you the solution. So in an orchard, let me explain to you the question. So in the orchard, there is 4 trees already, and there is about 20 durian per tree. So for every durian you add, for every tree that you add, 2 durians will reduce. Notice the -2. It shows the reduction of durian in one tree. So for every added tree, the durian will decrease by 2. What we're going to find is that we're going to find how much of tree that you add will maximize the production of durian, the total number of durian. So the thing that we want to maximize is the total amount of durian. So this AMT is amount of durian. So let's look at the equation that we have here. I'll represent D for the total amount of durian. Okay, so that equals to durian. We'll have number of trees times by the durian per tree. So basically, this So basically this equation will calculate the total amount of durian in all trees. So what we want to do from here is that we want to create an equation to find those amount. So what we'll do first is that we will let x equals to the additional trees added. So we can say that since that we have 4 trees already, so we can put 4 here, and then we can add x because x is additional trees. So if you're going to add more trees, you're going to put a variable x here. So this will calculate the number of trees, and then we're going to have another equation which is durian per tree, and that will be 20 for now. Sorry, that will be 20 per tree, and every time the tree is added it will minus 2, and we'll add an x behind to represent the multiplication of trees. So this is the equation to calculate the total amount of durian. We're going to use this equation to optimize, because we're going to optimize the total amount of durian. So we want to optimize this equation. Now in some of the question we have the constraint. In this equation we're going to skip the constraint. That's because we already have the equation in one term, which is x. We don't have a 2 term here, so we don't need a constraint from that. So like the other solutions, first we're going to actually differentiate this equation. But first we have to expand it. So when we expand it, we will get negative 2x squared plus 12x plus 80. And then when we differentiate it, we will get negative 4x plus 12. Now we're going to find the critical points. So we'll equate that equation with 0. We're going to factorize it. No, we don't have to factorize it, sorry. We're going to find the x, which is x equals to 3. So this is the total numbers of tree to add to maximize the durian production.